Okay, so now we are going to look at another sensory system, hearing. Okay, so we're going to look at the stimulus for hearing. We're going to look at the parts of the ear, and we're going to look at how transduction works in the auditory system, and a little bit about the auditory cortex. So what is the stimulus for sound? For hearing, rather. Well, of course, the stimulus is sound. What is sound? Well, sounds are created when objects vibrate. So the vibrations of an object basically cause molecules in the air around the object to vibrate as well. So these vibrations cause pressure changes in the medium, which is usually air. We're talking about human hearing. So these sound waves, these pressure changes rather, increases or decreases in pressure, create patterns that are called sound waves. So the sound waves that we hear are simply fluctuations in air pressure across time. So sound is both a physical and a perceptual quality. So the physical quality is the pressure changes that create the sound waves. The perceptual quality is, of course, the sounds that we hear. So the sounds that we hear are made up of many different fluctuations in air pressure over time, from nails going down the chalkboard to your favorite song, all just pressure changes across time. So your perception is your perceptual experience is based on these pressure changes over time. So sound waves have a couple of characteristics. So the couple of characteristics of sound waves are frequency and amplitude. So these are also qualities that are relevant to light waves as well. We didn't talk about light waves in the vision section, but whenever you're talking about waves of something, you're going to be talking about frequency and amplitude, and sound is no different. So frequency, when we're talking about sound waves, it's just cycles of pressure changes per second. And then, so you can see, let me get my cursor. So if we've got a low frequency sound right here versus a high frequency sound, the low frequency sound, fewer pressure changes, cycles of pressure change over time. High frequency sounds, more pressure changes over time. Now we can also have amplitude changes as well. So amplitude is the size of the pressure change. So if we've got a high amplitude, so we've got bigger waves here in this panel, we've got smaller waves in this next panel. So a loud and loud, of course, or sorry, amplitude is going to relate to our perception of loudness. So high amplitude waves are going to be really loud sounds, and low amplitude waves are going to be softer sounds. So amplitude, the size of the pressure change. So when we're talking about sound waves in the context of auditory perception, it's important to remember that the sound waves that we hear are complex, and they're going to be a mix of different frequencies, a mix of different amplitudes. They're comprised of simple, simpler sounds. So if you're looking at like something like simple sound waves, what are also referred to as pure tones, these are not something that you will come across in the natural environment. We're usually dealing with a complex mix of different frequencies and amplitudes. pure, like simple, pure tones are used in the laboratory to study auditory perception. But usually we're talking about more complex types of sound waves. So we know what sound is, a little bit of what sound is. Now let's look at how sounds are detected and recognized by the auditory system. So we're going to talk a little bit more about the auditory system than we did the visual system, because you've probably covered the visual system before, either in intro or brain and behavior, but you probably haven't looked at the auditory system. It tends to be neglected. So the sense of hearing has evolved over millions of years, and it can do some pretty amazing things. So we're going to look at quite a few different anatomical structures in the ear that are essential to understanding how sequences of tiny air pressure changes are turned into meaningful sound perception. So if you remember from your intro or brain and behavior, the anatomy and physiology of the eyeball may seem pretty complicated, but the ear is actually even more complicated. So from the outside, out here, the anatomy of the ear looks pretty simple, right? The outer ear, what we're used to seeing. But the process of transducing sound waves into neural signals is even more complicated and convoluted than the process of transducing light energy into neural energy. So we've got three divisions of the human ear. We're going to look at each one in turn. So we've got the outer ear, middle ear, inner ear. So let's start with the outer ear. So this is the pinnae. This is probably the part that you think of when you think about the ear. It's the outer part on the side of your head. So sounds are first collected from the environment by the pinna, pinnae for plural. So that's that curly structure on the side of your head. So its function is to collect and slightly amplify sound waves. And it also helps us to locate where sounds are coming from. So we're not going to talk a lot about auditory localization. We're not going to really talk about it at all. But I can say that it helps with auditory localization in the sense that if a sound hits your right ear before it hits your left ear, so if those sound waves hit your right ear, your outer right ear first before your left ear, your auditory system can use that information to say, well, it's probably closer to my right side if it's hitting my right ear first. Say the sound waves hit both ears at the same time, then they're probably coming from either directly in front of you or directly behind you if they're hitting both ears at the same time. So that's one way that our outer ear helps us with sound localization, just determining the timing of when sounds hit each ear. So that can be used to help us locate the source of sounds. So the pinna directs those sound waves into the auditory canal, and this leads us to the middle ear. Now, another function of the auditory, the ear canal, is to protect the very, very delicate tympanic membrane from damage. So sound waves are funneled by the pinna into and through the ear canal, and the ear canal only about 25 millimeters in length, so it only extends about 25 millimeters into your head. And the length and shape of the ear canal enhance sound frequencies between frequencies between 2000 and 6000 hertz. So they can ear canal enhances these frequencies in this range, but the main purpose of the ear canal, of the auditory canal, is to protect the tympanic membrane, which is a very delicate structure. At the end of it, the tympanic membrane, also referred to as the eardrum. So the auditory canal really provides a buffer zone between the delicate middle inner ear structures and the outside world. So the deeper we get into the ear, the more delicate these structures become. So the ear canal provides a buffer zone for these delicate inner structures. So the middle ear contains the tympanic membrane, which I just mentioned, and also the ossicles. So I've got this picture here, it's blown up so that we can see this a little bit better. So if we take this section out, blow it up, that's what it's going to look like down here. So let's kind of zoom in on that one little square. So the tympanic membrane, that is this section right here. Like I said, also known as the eardrum. The tympanic membrane, it vibrates in response to sound waves that are reaching it. So the tympanic membrane, it's a sheet, it's a thin sheet of skin. It moves in and out in response to pressure changes, the pressure changes of sound waves. So it's kind of almost like a drum. If you can imagine a drum, you hit the skin of the drum and it moves in and out in response to those pressure changes, kind of how the eardrum works. So it's a common myth that puncturing your eardrum will leave you deaf. So that's not true, but a ruptured eardrum can be extremely painful. But in most cases, a damaged tympanic membrane is able to heal itself just as other parts of the skin do. So it is a piece of skin, and it can heal itself as long as the damage is not extensive, so it is possible to damage the tympanic membrane beyond repair. So certainly a good idea to follow your mother's advice and not stick things in your ear. So with the tympanic membrane, those vibrations that occur in the tympanic membrane push and pull on the malleus bone. So that's this right here. So when this drum bump pushes in and out, it pushes the malleus bone. So that's this right here. So the malleus receives those vibrations from the tympanic membrane. So the malleus is the first of 3 ossicles. So the malleus it's connected to the tympanic membrane on one side, and it is connected to the incus on the other side. So the malleus, it moves back and forth as the tympanic membrane vibrates. And along with the other ossicles, the malleus works to amplify sound waves and transfer the energy of those sound waves onto the cochlea, which we'll get to in a minute. So the malleus, one of 3 ossicles. So the ossicles are those tiny bones in the ear. You've probably heard of the ossicles and the fact that they are the smallest bones in the human body. So the malleus is the first of these, attached to the tympanic membrane, moves in and out as the tympanic membrane vibrates, and then it moves the incus. So on the other side of the malleus, we've got the second ossicle being the incus. So the incus, it's attached to the malleus on one side and the stipes on the other side. And along with the other ossicles, the incus works to amplify those sound waves and help transfer the energy from the sound waves onto the cochlea. So incus attached to the stipes, which we'll look at next. So the stipes moves back and forth along with the other ossicles that are kind of in front of it. So these ones in front of it on the way out the ear. So the stapes moves back and forth, transferring the push and pull energy of the incus onto the oval window. So the oval window, it's kind of hidden in behind the stapes. You can't really see it in this figure, but I'll put another finger up in a minute where we can see the oval window. So transfers that energy onto the oval window. So the stapes, along with the other ossicles, works to amplify the sound waves and transfer their energy onto the cochlea. Okay, oval window. So I'm just wondering here, the oval window, it's hard to see in this picture as well. Okay, I might have another picture coming up where we can see it better, but okay, the oval window is the border between the middle ear and the inner ear. So the border between the middle ear and the inner ear. Now, the oval window is, it's a membrane. It's a membrane. It is on the outside of the cochlea. The cochlea is going to be this structure here, this coiled up structure. So the oval window is a membrane on the outside of the cochlea, and it's the boundary between the middle ear and the inner ear. So the stapes transmits those vibrations of sound waves to the oval window, which is just another membrane. So the oval window forms a border between the middle ear and the inner ear. So let's move on to the inner ear. So the inner ear is where the changes in sound pressure from the environment are translated into neural signals. The neural signals that are going to tell us what is going on in the world. So the function of the inner ear in terms of processing sound waves, it's similar to what the retina does with light waves in vision. So this is in the inner ear, this is where those sound waves are translated into neural signals. So the major structure of the inner ear is the cochlea. And the cochlea houses the delicate structures of the inner ear. It is this kind of snail-shaped structure. It's tiny, it's coiled up, it's embedded in the temporal bone of the skull. So when it's rolled up, the cochlea, it's about the size of a little tiny pea, so only about 4 millimeters in diameter. But when it's uncoiled, it is shaped like a tube and it's almost 10 times as long. So when you roll out the cochlea, it goes from 4 millimeters in diameter to 1.4 inches. Just to give you an idea of how much it is coiled up in the temporal bone of your skull. So with the cochlea, we've got kind of two ends that are important because how each end responds to different frequencies. So we've got the base. So the base is here. The base is near the stapes and the oval window. And the apex is this, you go round and round and around to the very inner part here. This is the apex. So it is in the center. So the vibrations that are transmitted through the tympanic membrane and those middle ear bones, those ossicles, cause the stapes to push and pull the flexible oval window in and out of the vestibular canal. So the vestibular canal is located at the base of the cochlea. So the movement of the oval window causes the sound waves to flow through the fluid in the vestibular canal. So the vestibular canal is fluid filled, and you can think of it as being similar to the way that the membrane of a loudspeaker moves air to create those sound waves. So the cochlea is it's a closed system. So pressure changes can't spread out in different directions. But what happens instead is that the movement of the oval window creates a bulge in the vestibular canal and extends from the base of the cochlea down to the apex, so down to the center. So the movement of the oval window creates a bulge in the vestibular canal, and this bulge travels through the cochlea from one end to the other. So if we look here, this is like a side section of the cochlea, or showing the vestibular canals. So because the vestibular, the canals, so we've got the vestibular canal, and we've got also the tympanic canal, and we've got the middle canal. So vestibular canal, tympanic canal, and middle canal. So the vestibular canal and the tympanic canal, they're tightly wrapped around this middle canal. And when the vestibular canal bulges, it causes, it puts pressure on the middle canal right here. So this pressure from the vestibular canal onto the middle canal causes another important structure to become displaced, and that is the basilar membrane down here. So the basilar membrane, it is located at the bottom of the middle canal, so right in here with this arrow pointing to it. So the basilar membrane will be pushed down, so it gets pushed down by the middle canal when the vestibular canal, that bulge in the vestibular canal is created. So this bulges, it creates pressure on the middle canal, and that causes the basilar membrane to move. So the basilar membrane, it's thicker and stiffer on one end, and it is thicker and thinner and more flexible, rather, on the other end. So this will be important, kind of the thickness and thinness of each end of the basilar membrane will be important. It's important for coding frequency. So let's look at how transduction sound waves works. So this is a cross section of another inner ear structure, which is called the organ of Corti. So movements of the cochlea are converted into neural signals by the structures located in the organ of Corti. So that's this right here. And down here, this is the basilar membrane. So if I just switch back to here, so we can kind of think about taking this little section right here and blowing it up in this next figure. So that's what this is. So if I switch back, down here's the basilar membrane, here's the basilar membrane, and then everything above it. So the organ of Corti extends along the basilar membrane, and the organ of Corti, it's made up of kind of a structural system of cells, and this system of cells support the neurons and dendrites and the auditory nerve fibers that are all in the organ of Corti. So these neurons are called hair cells. So that's what these little things are here. These are hair cells. And the dendrites of the auditory nerve fibers basically terminate at the end of these the end of these hair cells. So these hair cells are important. These hair cells are the receptors for hearing. So the hair cells are what transduce movement in the inner ear and convert that movement in the inner ear into neural activity. So these hair cells, they provide the foundation for little minuscule hair-like bristles that are called cilia. So the cilia, they're like bristles that protrude from the tops of the hair cells. And these bristles will move in response to changes in sound pressure. So kind of like the photoreceptors in the retina, hair cells are specialized neurons that transduce one kind of energy, in this case sound pressure, into another form of energy, which is neurons firing. So the hair cells in the vestibular organs also give our brain information about head movements, and this is important for the vestibular reflex. So the movement of the hair cells, the cilia on the hair cells, causes a change in membrane potential that initiates the release of neurotransmitters. So there's two types of hair cells. Sorry, before I skip ahead, so we've got inner and outer hair cells. So inner hair cells, here's an inner hair cell, outer hair cells, these are these ones. And they are arranged in rows. So let's just look at these hair cells and how they are arranged, the inner and outer hair cells. So these hair cells are arranged in 4 rows that run down the length of the basilar membrane. So 1, 2, 3, 4. We've got 4 rows run down the length of the basilar membrane. So we've got 1 row of inner hair cells here, and we've got 3 rows of outer hair cells running down this way. So another important structure for transducing sound waves is the tectoral membrane. So that's this right here that I've got outlined in black. So the tectoral membrane, it extends on top of the organ of Corti. And it's not really a membrane, just like the basilar membrane, it's not really a membrane. It's called a membrane, but that's just the name. So the tectoral membrane, it's also not a membrane. It's a squishy flap that is attached on one end and floats above the outer hair cells on the other end. So it's attached here, but it's floating out here above those outer hair cells. So the taller of the hair cells, the taller cilia rather, of the outer hair cells are embedded in the tectoral membrane, and the cilia of the inner hair cells are kind of nestled against it. So we've got the taller cilia of the outer hair cells being embedded against the membrane, and then these inner ones are nestled against it because of the way that it's attached here and just floating here. So each of these cilia, okay, so now we've taken kind of one of these hair cells and we're going to blow it up and see it in more detail. So each cilia has something called a tip link. So that's this tip link on top of it. So these tip links connect the hair cells to their neighbors. So they're connected by the tip links and they bend together as a set when they are deflected by the motion of the tectoral membrane. So you can imagine with the tectoral membrane being attached on one end and floating freely on the other, that the movement of the inner ear is going to create, you can almost imagine it like taking a sheet and flinging it out, right? You're holding it in your hand, the other end is loose. So it creates kind of like what is called a shear force because of the way it's attached at one end and loose at the other. So the tip links, they're connected together. And they will bend together as a set when they are deflected by this shearing motion of the tectoral membrane. So the tip link pulls on the taller of the cilia, and this will open ion pores. So when they are, when the pore opens, this allows, so when the hair cells are stretched, it opens up these ion channels. And then what happens when the ion channels open? We can have positively charged ions flowing into the cell. So this is going to change the membrane potential of the cell, and it's going to cause the release of neurotransmitters to be released into the synapse between the hair cells and the auditory nerve fibers. So the tip links, they are bent by the shearing force of the tectoral membrane. This stretches them, it opens up channels. So like if the shearing force is going this way, it's going to stretch the channels this way. It's going to open this channel, mechanically open it, and allow, say, for example, sodium to flow in. And this is going to increase the charge of the cell, bring it closer to, firing a signal. And this is going to stimulate neurotransmitter release. So that's the forward motion of the tip link. And then what happens is that the backward motion, because remember the tectoral membrane, it's flipping around out there, so it's going to come back. And that backward motion is going to close the channels. So this back and forth bending causes alternating bursts of electrical activity. So different places on the cochlea are tuned to different frequencies. So this is referred to as the place theory of hearing. Place theory meaning that different frequencies will stimulate different places along the cochlea. So if we were to take the cochlea, and of course the basilar membrane is tucked up in there as well. If we were to take that, remember how we said it was all coiled up? So if we were to take that and uncoil it and look at it like this, you can see here that we've got our narrow, thick base near to the middle ear section. And then this is the apex, that is the innermost coiled up area. So the basilar membrane, it is thick and stiff on this end, and it is thinner and more flexible on this end. So different parts of the basilar membrane are tuned to different frequencies. So that narrow, thick base, it is tuned to high frequencies, whereas the thin and much wider apex, or middle portion, is tuned to lower frequencies. So high frequencies cause the largest displacement, the largest movement near the base of the cochlea, while lower frequencies cause displacements further away near the apex. So different places on the cochlea are tuned to different frequencies, and this tuning is described as the place code for sound frequency. So information about a particular frequency of an incoming sound wave is coded by the place along the cochlea with the greatest mechanical displacement. So high frequencies cause the largest displacement closest to the oval window near the base of the cochlea, while lower frequencies cause displacements further away near the apex. So this kind of map of different frequencies that we can see in the cochlea, with one end being tuned to high frequencies, one end being tuned to low frequencies, and then what we get is a grading in between of slight different parts responding to slightly different. So here you're going to get up here, this part of the basilar membrane responding to slightly lower frequencies, and slightly lower and slightly lower and slightly lower, and all the way out to the end. So it's a gradual change in which type of frequency each part of the basilar membrane prefers. So this arrangement, of frequencies that happens, along the cochlea and the length of the basilar membrane, this organization is maintained all throughout the auditory pathway. So this should be sounding pretty similar to what happens with vision. So the frequencies are arranged according to the frequency along the length of the cochlea, and this organization, it's maintained all throughout the auditory pathway. So we're not going to talk about the midbrain, brainstem, and midbrain structures in the auditory pathway. We're going to jump right ahead to the primary auditory cortex and just kind of look at how this organization is maintained. So if you were to take a little spatula and kind of pry open the temporal lobe, so if you were to take the Sylvian fissure and kind of pull it down and pull this part up, you'd be able to see the auditory cortex right in here, the primary auditory cortex. And what you get is an arrangement that basically is the same as what you see in the cochlea. So we've got this part here responding to the same frequencies as the apex of the cochlea, so that inner part. And then you've got all the way up at this end, you've got this end corresponding to frequencies that are received by the base of the cochlea. And then you've got everything in between in a very organized fashion. So this is referred to as tonotopic mapping. So, you've got retinotopic mapping in the visual system. We've got tonotopic mapping in the auditory system. And it just means that those frequencies are arranged from lowest to highest. They're arranged in the cochlea, and this organization is maintained all throughout the auditory pathway. So all of the structures in the auditory system, beginning with the basilar membrane and continuing throughout brainstem and midbrain structures, all the way up to the auditory cortex, show a pattern of organization that is based on the frequency that they are most sensitive to. So cells in each of these structures are arranged in such a way that the neurons that respond to a particular frequency are close together, and other neurons that have a slightly different frequency preference are slightly further away. So neurons that are most sensitive to low frequencies are located at one edge of the structure, and neurons that respond to high frequencies lay on the other edge. And neurons responding to other frequencies are spread out in an orderly fashion in between. So we have a gradient of frequencies that are represented by adjacent parts of each structure in the auditory system. So the frequency preferences shift just slightly. So this tonotopic organization, it starts in the cochlea, it's maintained all the way through to the primary auditory cortex, but it does start to become less precise once you get to A1, so not as precise as what is seen in the basilar membrane and in the cochlea. And then once you get into those secondary auditory regions, it becomes even less well maintained. But up until the primary auditory cortex, pretty good mapping. So what we can say about the auditory pathway, just a couple of last little points before we watch a video that shows us the journey of sound through the ear. Give you a nice little visual of all the stuff we just talked about. So we do have crossing over of auditory information to each hemisphere, just like we do with the visual system. So most of the auditory information does cross over to the contralateral hemisphere, and we also have some information maintained on the same side, just like with the visual system. And this, of course, means that each hemisphere receives information from both ears, very similar to the visual system. Okay, so let's wrap up the auditory section, watch a video, and move on to our next one.